by float zone technique, which is sort of like a zone refining of the same principle. So a float zone can be done very nicely in space because there is a great vacuum and things can float because there is no gravity. So one can have a zone which is melting to any desired thickness you want. But and anything which is done outside the space environment, which we are not, we are doing experiments inside the space lab, which is a shirt sleeve environment. Astronauts, have you seen? They are just wearing shorts and running around. But if you do experiments outside the shuttle in the Bay Area, then the vacuum is very low. It's 10 to minus 14 torr. So there are some experiments are done outside because, for example, there is an experiment to detect gamma rays. That instrument was placed outside the space lab. And so these are, and then the next question was that why we chose TGS. The dielectric loss is expected in the space-bound crystals, which is what we expected. The dielectric loss in crystals is because of domain relaxation, because TGS crystals have electrical dipoles, they are plus minus, and they are all randomly oriented. So if they are all arranged in a proper fashion, then the crystal will give better quality. So the domain relaxation is due to that, and the microscopic solution and air inclusions during crystal growth. Like if you grow a crystal and if there is an air bubble sitting on the seed crystal, the crystal will grow around the air bubble. So there will be inclusion. This is what we call as an inclusion, air inclusion. So this can be, and that gives effect because when you put a laser beam through it, the light will scatter, and you don't want scattering to take place like that. In space, due to the mainly diffusion control environment, the position is ordered. There are few microscopic solution and air inclusions, less strain centers, so domains will be more mobile. So we expect low dielectric loss and improved figure of merit for these crystals. We use this technique of a unique cool distinct technique for solution crystal growth. The reason is that because, as I said, the TGS has a positive temperature coefficient. If you look at the solubility curve of TGS, the curve goes like this. As the temperature goes up, the solubility changes in a positive way. There are materials, as I mentioned on Friday, there are some materials which have negative solubility. And typical material is lithium iodate. Lithium iodate, if I want to grow crystal, instead of lowering the temperature, I need to raise the temperature because it has a negative solubility curve. So what TGS is like. And so the normal solution growth techniques are not very susceptible to growth in the space environment. So the cool distinct technique was conceived and the crystals were grown on these two phases 010, which is the fastest growing phase in TGS. This is a summary of the experiment. We ran experiments on a cool distinct, which I'll show you in a minute later. Should have been at 4 actually. Cool distinct is a rod, and on this rod at the end of this tip, the seed crystal was mounted to grow, and this seed was actually cooled by a thermoelectric cooler. Thermoelectric cooler was somewhere here, and that cooled the seed. So if I maintain the temperature of the solution at a constant temperature and just cool this tip, the seed becomes cooler. So that actually becomes a driving force. The solute tries to move towards the cool region and the crystal grows. And when this technique was conceived in our lab here, I didn't have any big instrumentation or big lab here. Even the machine shop didn't exist much here at that time. So the first time when we tried this technique, I took a copper tube, put a seed crystal on the end, and passed liquid nitrogen through the tube, and put a microscope to see that what is happening to this crystal, and put this seed in a solution. And when I passed the liquid nitrogen, I saw immediately on the microscope that the crystal was changing as a function of time, that there is a growth there. And I said, aha, this technique will work. So then we designed a sophisticated instrument later on to grow crystals, and then we sent the paper to the journal, and it was published, and the technique works. Now that this is the only technique which can be used for solution growth in the space environment. So we ran two experiments in this space. One is the sting temperature was equal to the fluid temperature, because they are same temperature, which was less than saturation. So the saturation temperature is 40 of the solution. The sting temperature was below saturation. That means crystal can grow. If I want to dissolve the crystal, then I can make this to be higher. Because in thermoelectric cooler, if you pass current and you reverse the direction of the current, one end of thermoelectric cooler becomes hot and one becomes cold. But if you reverse the current, the effect is opposite. So if I want to cool the crystal, I pass current in one direction. If I want to heat the crystal, I want to pass current in the opposite direction. So this is a good technique to even dissolve the crystal or to grow the crystal. So it works out pretty good. And we use the holographic optical elements to monitor. And then another run we had 001 crystal. See, this is a phase which is the slowest growing phase in TGS crystal, but is the largest phase. When I show you the crystal morphology. So we also grow crystal on this phase to see that what is the difference between the growth rate on this phase as compared to the growth rate on the fastest growing phase. This is the morphology of TGS. This is the 001 phase. If you look at it, this is exactly the crystal looks like. If you go to the lab downstairs with Padmaja, you will see some TGS crystal sitting. This is exactly the morphology. This was a crystal made out of, when we made this diagram, this was published in a book article which Dr. Agrawal published a few years ago. And this diagram is taken out of the book. But this is a slowest growing phase. This is the 010 phase here. It's not pointing to the light. Labeling is correct. 010 cut cleavage phase.
There is an arrow.
This is the arrow here. Where is the arrow?
The second arrow, yes, vertical arrow.
So this is 010. Yeah, this is the arrow again. So this is the 010 phase. So this is, so what we did when I say by natural phase, that I cut a crystal, seed crystal, parallel to the phase on the back side. That means the phase which was used for growth was natural. The phase which was used cutting was cut phase, and the cut phase was actually glued to the string. So the growth side was natural. So we had one seed like this from 001, other was 001, which was another crystal which was cut parallel here, and we put this was about a millimeter or 2 millimeter thick disc or a size, which is shown here and shown here. And this was attached to the string, which is this point, and this is a copper, and there is thermoelectric cooler here. So if you look at the string drawing, this is the copper rod, and this is thermoelectric cooler here. And the electrical wires are coming out and going to a power supply and so on. So if I put the direction of the current in one direction, I can make this phase either cooler or hotter. So if I want to dissolve the crystal, seed crystal, then I have to pass current in a direction so that this tip becomes hot. And the reason of making this hot is that in solution growth crystals, anytime you grow a crystal, you need to dissolve the seed crystal before you start growing. And the reason of growth is that there's always some defects on the surface. Even a natural surface might have some particles on it or something which are stuck. Although we do all the work in clean room, but still. So in that case, we always, before we start the growth, we do heating of the seed crystal so that some surface, few microns are dissolved. And then we change from dissolving to the cooling side, and then the crystal starts growing. So then we change the direction of the current. So one thing is learned from this series experiment, that the transition from the solution to growth is very, very uniform in a space environment. On the ground, it is very abrupt because the gravity helps to change the current temperature very easily. So on the ground, it is very abrupt. And that's why the crystal always have defects. But in space it is very uniform. So we change the temperature, we dissolve the seed crystal, and then change the direction of the current. And this was not done by hand. We developed, it turns out that the temperature profile of maintaining the string temperature is a third order polynomial. And in third order polynomial, we completely determine all the constants and fed into the computer, and the software is developed for that. So once we start the experiment, we feed this thing with that work, and then it maintains and goes from heating to cooling and so on. But when the crystal size also becomes bigger, you need more heat, more cooling, because crystal becomes a little bigger. So the polynomial actually takes care of the entire cycle for the experiment time. And you see that there are air here. This air is actually used for insulation purposes. And this is the plexiglass. This was built actually by Lloyd Sharp, Carlin's father, in his lab during mission time for our lab experiments. But the same thing was built by TRW in Redondo Beach, California for the flight. The only difference was that in our lab, this thing was built for about $500, and for the flight experiment, it costed $2 million. This is a system which is in the cell itself. This is the.
What you built in for lab and for the flight, but otherwise they were identical.
Otherwise, they had the same profile. We gave TRW the science requirements. We said that this thing should maintain it at certain temperature, plus minus so much. But one thing is good to know, that one does not realize very easily that in a ground, the crystal growth chambers or the controllers are very sensitive. Because we need to maintain temperature of the order of plus minus 0.01, because we don't want too much fluctuation. But in space, one can do 0.1, because the reason is there is no gravity. So even if there is a change in temperature of 0.1, it takes long time for the temperature to reach the seed crystal, because there is no convection. Very simple. So as a matter of fact, our requirements for the shuttle are less stringent than the requirement for the ground experiment. The ground experiment, even if we like to have 0.001 accuracy of our temperature profile.
You could have used $500.
Could have used $500. Yeah. But the only thing is that
space qualification.
Yeah.
Everything has to be space qualified.
Space qualified. Just like a light switch which you have here. That switch costs $1 in Home Depot. But a switch like that, once it is done for space, costs hundreds of dollars, thousands of dollars. Because it has to be tested. We have absolutely no chance of failure to our best. But we still do fail. So this test goes through.
And then I guess it has to have backup. Fail proof or there's a backup.
They do testing of this switch, turning off and on for thousands of times, and then make sure that doesn't fail. So this is a chamber which is on the ground. We maintain the water bath, and this is the inside chamber where the crystal will go, and the seed crystal is mounted here, and then we go from there to do the crystal. Just like very simple, like you first heat the crystal, this is all part of it, and then cool it, so the crystal starts growing and a layer is grown on the surface of this seed crystal itself. This is another technique, the normal technique of growing in the ground. This is a reciprocating solution. Here the chamber is here, this is a water bath. The seed crystals are mounted here, and we rotate this at a programmed rate, and then rotate it in one direction, and then after a while we rotate it in a counterclockwise direction. And then you might ask the question that why we do that? Why can't we just rotate in one direction? And the reason is this, that this seed crystal which is growing, when you rotate the crystal in all the time in one direction, there is a trailing face, this is a front face. So the crystal actually grows on this face, and this face doesn't grow. And we don't want that. We want the whole crystal to grow uniform. So we rotate in one direction and then reverses the direction. And this device was built in our lab, and it has been published. I think Dr. Agarwal and myself we have published in Journal of Scientific Instruments, electronic device by which we can change the direction at a regular rate. This is the experiment which was shown